Here we have an area bound by the function y equals minus x squared plus 1. Here's our x-axis, here's our y-axis. And the area is the area under this curve, so it's bound by the x-axis and the y equation. It goes from 0 to plus 1 to minus 1 and 1 on the y-axis, if we found that intercept. We're being asked to find the moments of inertia about the centroidal x and y axes of the shape. So first off, we'll have to find the centroid, and then we're going to find the moments of inertia about the original x and y axes, and then we'll use parallel axis theorem to transfer them to the centroidal axes. So to find the centroid, we can say that we know x bar, the distance to the centroid from a known location, is equal to the integral over the area of x tilde, which is the component moment or component centroid, dA, divided by the integral of dA over the area. And let me just say what we'll be doing here then is we'll approach this problem by taking a series of strips, and it's easiest for us to take strips in the vertical direction for this problem. And the reason we'll take strips is this will allow us to convert this area, this integral over an area, into single integration about the x direction. So it'll be with respect to x, or dx, involved in there. And we'll see how we do this in a second. Now it's much easier for us to convert this into vertical strips than it is into horizontal strips due to the nature of the function. If we were to do horizontal strips, we'd see that we'd need to solve for x in terms of y, and to do that we'd end up with two roots of this equation, so it's a little bit difficult to approach it that way. If we draw a strip of width dx, and we know dx is an infinitesimally small width. As dx approaches 0, that width approaches 0, obviously. In this strip, we'll have a height of y. So the height between the x-axis and the function itself is y. And the location in the x direction, we will have x tilde, which is the distance from 0 to the centroid of that strip. But that will be equal to x as dx approaches 0. And the centroid of a rectangle we know is at y over 2, so we'll have another thing that we can find here. So here we have the height from 0 to the centroid is y tilde, and that's equal to y over 2. And then finally we can calculate the area of this strip. So we can say dA is equal to y dx. So the differential area of that strip. And if we wanted to expand that, now we can sub in some stuff. We can go dA is equal to, well, we know y as a function of x already, so minus x squared plus 1 dx. Okay, so we've defined the area of a strip as a function of x, and now you can see that if we take an infinite number of vertical strips and add them all together, we'll have the area. So in other words, if we integrate dA, we get area, and that just means we have to integrate minus x squared plus 1 with respect to x. And we can also apply the first moment of areas. So x tilde, the distance to the area, multiplied by the area divided by the total area, will give us x bar. That's the first moment of area theorem. So here we can say, well, first off we'll note, we know x bar will equal 0 by symmetry. If we folded this shape along the y-axis, it would be mirrored on the left and the right, and that's axial symmetry. We have single axis symmetry. That means we know the location of the centroid falls on that axis of symmetry, which is the y-axis. But we will find this, we will calculate it anyway. And this is just as part of a teaching example. We'll go through the effort of calculating this 0 value. So if we compute this value, we could say that x bar is equal to, now we want to convert this integral over the area of x tilde into a single integration function. So instead of integrating over the area, let's integrate over x from -1 to 1. And we know that x tilde here is x. And if we want to integrate over x instead of dA, we need to sub in a function of dA, or an equation for dA. So that's y dx. And all that will be divided by the integral of dA with respect to area, which is the same as the integral from -1 to 1 of y dx. And as we stated up here, dA is y dx. And then we can sub in our function of y, as we did up there. And we can integrate from -1 to 1 of x times y dx, which is -x squared plus 1 dx, over the integral from -1 to 1 of -x squared plus 1 dx. And if we compute that integral, we will get x to the fourth, negative x to the fourth over 4, plus x squared over 2 from -1 to 1, all that divided by -x cubed over 3 plus x from -1 to 1. And if we stub in our discrete points into this integral, and that way we'll be calculating the area under this curve, we can see for the bottom point, and we'll be calculating this area times x bar for the top point. We can see that x bar is equal to -1 over 4 to the fourth power, so that's negative, and then the 1 in the brackets, plus 1 over 2 squared minus 1 to the fourth over 4 plus -1 squared by 2. All that will be divided by -1 cubed over 3 plus 1 minus -1 cubed over 3 plus -1. A little messy there. It's plus -1. And we can see that if we multiply this out, we would end up with 0 over a quantity, and that quantity would be -2 over 3 plus 2. In other words, we would end up with x bar is equal to 0 over 4 by 3, which is obviously equal to 0, but this 4 by 3 means something to us. Recall that we had area is equal to the integral of a dA. So area is equal to the integral of dA with respect to area. And that's simply equal to now 4 over 3. So now we know area. We can put that in our pocket and take it out when we need it a bit later, when we're calculating y bar and when we're also applying a parallel axis theorem at the end. So we can say x bar is indeed 0. And as we knew it would be, based on our knowledge of symmetry. So that was the easy part of this example. Now we'll move on to determining y bar. And y bar is equal to the integral over area of y tilde dA divided by the integral over area dA. See, we already know that value, so we'll just be able to use it directly in. So I won't expand this term because we know it's 4/3 already. And this is equal to the integral over area. We know that y tilde is equal to y over 2 dA over the integral by area dA. And if we expand that again, we can substitute in x for our y value there, and we can see we're still working in the integral of area minus x squared plus 1 over 2 dA. So So we just subbed in, for this y, we subbed in the equation of y, which is minus x squared plus 1 over 2. All that's divided by the integral of dA. And then we can plug in, or convert this into a single integration, so we'll convert it for minus 1 to 1 of minus x squared plus 1 over 2 times what we calculated for dA, minus x squared plus 1 dx. So the integral from minus 1 to 1 with respect to x of that quantity divided by integral of area dA. And we can compute that out, and we'd see that y bar is equal to 1/2, and here we're still working, if we expand that and collect like terms, we'd have x to the 4th minus 2x squared plus 1 dx. And that would be divided by what we calculated, the integral of dA is 4/3. So we can start plugging in the values for that, and we'd see that's equal to 1/2 times x to the 5th by 5 minus 2x cubed over 3 plus x, and this is from minus 1 to 1. All that will be divided by our area, 4 over 3. And if we plug in our values for that discrete integral, we get y bar is equal to 3 over 8 times 1 over 5 minus 2 over 3 plus 1 minus negative 1 over 5 plus 2 over 3 minus 1 is equal to 3 over 8 times 8 over 15 plus 8 over 15. Oops, should keep the same style brackets. Now at this point we can just solve for it, and we get y bar is equal to 2 over 5, and that's equal to 0.4 meters, and x bar is equal to 0. So here we have the equations for x bar and y bar, and our distances to the centroidal axes of that shape. So I've redrawn the shape down here, and we see our original axes, and then if we move up a distance of 2 over 5 and draw in our centroidal axes, we have a centroidal coordinates of 0, 0 at our original coordinates of 0, 2 over 5. And our original equation, or the equation for this curve in our xy coordinate system, is y is equal to minus x squared plus 1. If we wanted to rewrite this curve in our y prime or x prime y prime coordinate system, it would be y prime is equal to minus x prime squared plus 3 over 5. So that 3 over 5 comes from the y-intercept in our y prime axis. As we move on in this problem, we're going to want to find the moments of inertia about the x and the y axes in the original system first, because it's pretty simple for us to calculate those. Later we'll apply the parallel axis theorem to transfer the coordinate system up to our local centroidal coordinate system. So to calculate the moment of inertia in x and y, so the x and y of our original system, we'll use the same strips. And what we know is that we know the area and all the distances away, so this is just a free body diagram of one of those strips. And that if we take the simple integral of x squared dA, so as dx goes to 0 here, we end up with just an area times a distance squared. And if we sum all those up, we are going to get Iy. And that's because all of the areas are in that strip have the same moment arm. So we're taking the second moment of area, and all the moment arms are the same. The y bar or the x bar values are the same. The same can't be said about the moment of inertia of the x-axis, because we have a centroidal axis of this shape, and it's offset from the axes about which we're taking the moment of inertia. And as dx goes to 0, we still have a centroidal axis that contributes to the moment of inertia of this rectangular shape. So to do this, then we're going to need to compute the differential moment of inertia, so dIx is equal to the moment of inertia of this strip of width dx plus the area times y bar squared. And we know that when we're computing, I'll do this in a different color, when we're computing d I bar x prime, so the moment of inertia of this strip, and it's the first differential of that because we're dealing with an infinitesimal width here, we can still say that this is equal to 1 over 12 times the width times the height of that rectangle cubed. And we can say that dA times y bar squared is equal to, well, y bar is y over 2, and that will be squared, times dA, and we calculated dA is y dx. So we have equations for dA and di bar x prime. Now, if we wish to avoid this parallel axis theorem problem for these perpendicular segments, we could instead draw horizontal bars across the shape here and compute simply the integral of y bar dA to get moment of inertia about this axis. So we could do vertical for the moment of inertia about the y-axis and horizontal about the x-axis. But converting this into a horizontal strip is a little bit of a trouble, as I said before, because the mathematics turns out relatively difficult when we convert this equation as a function of y instead of a function of x, since there's two roots to this equation. So let's apply this equation here, d differential of the moment of inertia. So differential moment of inertia for a single strip of this is equal to the moment of inertia of the strip itself about the strip centroidal axis plus the dA y bar squared term. Now to find Ix, we will work with the dIx is equal to di bar x prime plus dA y bar squared equation. And if we take that equation and we plug in what we solve for here for di bar x prime and dA y bar prime, we can see that dIx is equal to 1 over 12 dx y cubed plus y squared over 2 y dx. And then, just in case that wasn't clear here, I'll just say that this is di bar x prime, and this is all the way over here is dA y bar prime squared, or y bar squared. And then we can multiply this out and collect like terms, and we can see that di bar x is equal to 1 over 3 y cubed dx. So this means that Ix is equal to the integral over the area of, or since now we're working in x terms, over minus 1 to 1 of dIx is equal to the integral from minus 1 to 1 of 1/3 y cubed dx. And we can plug in our values for y that we know, so this is integral from minus 1 to plus 1 of minus x squared plus 1 over 3 cubed dx. And then we can solve for that, so we'll expand that and collect like terms, and we have Ix is equal to 1/3 onto the integral from minus 1 to 1 of minus x to the 6th plus 3x to the 4th minus 3x squared plus 1 dx, and that's equal to 1/3 minus x to the 7th by 7 plus 3x to the 5th by 5 minus x to the third plus x from minus 1 to 1. And this gives us Ix is equal to 1 over 3 times minus 1 over 7 plus 3 over 5 minus 1 plus 1 minus 1 over 7 plus 1 over 7 minus 3 over 5 plus 1 minus 1. And we get Ix is equal to 32 over 105, which is equal to 0.30476. So we've just computed the moment of inertia of this shape about the original x-axis, not the x-centroidal axis. Now we can find Iy, and in this case it's just going to be Iy is equal to the integral of x squared dx, because all of the integral of x squared dA over the area, because all of the strips have the same x bar, and so they all have the same moment arm, meaning that we can simply sum the second moment of the area. We don't need to take the component moment of the inertia into effect. And if we have the integral over area of x squared dA, we want to convert this into single integration, so we can say this is the integral from minus 1 to plus 1 of x squared, and then we know an equation for dA is minus x squared plus 1 dx, and this is equal to the integral from minus 1 to 1 of expanding this out and collecting like terms. We have minus x to the fourth plus x squared dx, and this can give us Iy is equal to, if we integrate this and apply our bounds, we can get minus x to the fifth by 5 plus x cubed by 3 from minus 1 to 1, and subbing in those values we get minus 1 over 5 plus 1 over 3 minus 1 over 5 minus 1 over 3. And this gives us Iy is equal to 4 over 15 is equal to 0.26667. So those are the moments of inertia about the x and y axes of the original system, which we can see here. We have the x and y axes of the original system, and we found the moments of inertia about the x-axis and about the y-axis. Now we want to transform them to this centroid here. So to do that, we're going to have to apply the parallel axis theorem. So now that we have moments of inertia about we have moments of inertia about axes that are parallel to our centroidal axes, we can find moments of inertia excuse me, about the centroidal axes using parallel axis theorem. So we can say that Ix, which we've just found, moment of inertia about this value, could have been calculated as the moment of inertia about the centroidal axis of that shape plus the area of that shape dy squared. And Iy could have been found as the moment of inertia about the centroidal shape of that, or centroidal axis of that shape, plus area dx squared, where dy and dx are the distance between the centroidal axes in the x and the y directions. So Ix is about x, and I bar x prime is about x prime, moment of inertia about x prime. And we can say the same with y. Iy is about y, and I bar y prime is about y prime. So if we know that, we can simply apply the parallel axis theorem sort of backwards from how we might normally approach it, by instead of solving for it at a axis that's separated from our, or instead of finding our centroidal axis property first and then applying it at a different axis, we will solve for our centroidal properties by rearranging this. So if we want I bar x prime and I bar y prime, which we do, the moments of inertia about our centroidal axis, we will take I bar x prime is equal to Ix minus a dy squared. So we'll rearrange this equation and solve for I bar x prime. And the same with I bar y prime is equal to Iy minus a dx squared. And once we have that, we're ready to go. We know all the components of these equations already. We know all the components except for what we're solving for. We know that I bar x prime is equal to Ix was 32 over 105 minus area, we calculated a long time ago, we had 4 over 3, and times dy. And let's go back to this page here, and we can say dy is the distance between the parallel axes. So there is 2 over 5 distance between those parallel axes. So minus times dy squared. And this is equal to 16 over 175. In other words, I bar x prime is equal to 16 over 175 is equal to 0.091429. And that's the final answer for the moment of inertia about the x centroidal axes of this particular problem. Now we want the moment of inertia about the y centroidal axes. It happens to be collinear with the y axes of the original problem. But let's calculate it anyway. We can get Iy, I bar y prime is equal to Iy we found is Iy we found is 4 over 15. That minus area 4 by 3 times the distance between the y prime and the y axis in the x direction is 0 squared, and this is 4 by 15. In other words, I prime y, or I bar y prime is equal to 4 by 15 is equal to 0.26667. And the units for these, well, they're unitless. I didn't make any units in the problem, but if this was in millimeters, they would be in units of millimeters to the fourth. If it was in inches, they'd be in units of inches to the fourth power of length. So as a summary, in case anything was unclear, to solve this problem, we had to first find the centroid in the x and the y direction, and while we were finding the centroid, we found the whole area. Once we knew that, we found the moments of inertia about the x and the y-axes. When we found it about the x-axis, since we had vertical strips, and those vertical strips had offset centroids, we had to calculate the strip moment of inertia over an infinitesimal width and add that to a d y squared. So we found the moments of inertia about this axis and this axis. And then when we did that, we then transferred them up to the centroidal axis using parallel axis theorem.